Well, hello again, fellow mathematicians. This is recording 1B for absolute value equations in Unit 7, Chapter 7 of Mathematics 2200. We'll be solving absolute value equations algebraically. Let's see, solve algebraically. The absolute value of negative 3x minus 6 equals 3. If you recall in the last recording, we did this one by graphing the left side, which was this graph, and the right side y equals 3. And the points of intersection were at negative 3, 3 and negative 1, 3. So that means the solutions, which are the x-coordinates only, negative 3 and negative 1. Let's see if we can get those same solutions algebraically. Okay, this particular equation follows this format. The absolute value of an expression, we'll call it expression 1, is equal to expression 2. Now recall from our earlier work on piecewise definitions for absolute value expressions, the absolute value of an expression is equal to itself if that expression is already 0 or greater, and it's equal to the negative of itself if that expression is already negative. So when solving this equation, this gives us two cases to consider. The positive version of negative 3x minus 6, that expression is equal to 3, and the negative version of that is equal to 3. And we solve the resulting equations. So here this positive here is not going to make any difference, so I'll move the 6 across. I get 3 plus 6 is 9. Divide both sides by negative 3, I get x equals negative 3. Over in case 2, I distribute my negative first, and I get 3x plus 6 equals 3. Subtract 6 from both sides, I get 3x equals negative 3. Divide by 3, and I get x equals negative 1. So I can see that these agree with my graphical solution. However, we don't always have the graphical solution available easily anyway. So we can do one of two things. We can figure out the restrictions from the piecewise function, which I'm not going to do here, or we can check them in the original equation to see if they work. So on this next slide, I'll substitute negative 3 in to the original equation to see if I get something equal to 3. I got 9 here minus 6. Absolute value of 3 will be 3, so we're good. Substituting in the negative 1, I will get negative 3 inside my absolute value symbols, but that's okay, because the absolute value of negative 3 is still 3. So both x equals negative 3 and x equals negative 1 are solutions. We did this one in our last recording as well, and we got the solution to be x equals 2. Only one point of intersection. Let's see what happens here. Inside the absolute value sign, the expression is x plus 5, so we have the positive of x plus 5 equals 4x minus 1. And then we have the negative of the expression. The negative of x plus 5 equals 4x minus 1. So we've got x plus 5 equals 4x minus 1 in the first case. That positive sign there doesn't make any difference. So I'll bring this minus 1 over to the left with the 5, and the x over to the right with the 4x. And I've got 6 equals 3x, and divide both sides by 3, I've got 2 equals x. Well, that one agrees with our graphical solution. Let's take a look at case 2. We've got negative x minus 5 when I distribute the negative through, and rearranging negative 5 plus 1 will equal 4x plus x. That gives me negative 4 equals 5x. Dividing both sides by 5, I get negative 4/5 is equal to x, or negative decimal 8. When I check my first solution, I get the absolute value of 7, which is 7, equals 4 times 2 minus 1, which is 7. So this one's good. But when I check the negative 4/5 solution, plug it in, I get common denominators inside here. I get the absolute value of 21 over 5. Here I get negative 21 over 5 when I do the calculations. So I don't get balance, therefore x equals negative 4/5 is extraneous, while x equals 2 is a solution. For our final example, the graphical solution showed 3 points of intersection, so 3 solutions, -1, 0, and 4. So we break this up into our cases as before, the positive of x squared minus x minus 2, and the negative of that expression. Rearranging case 1, because it's quadratic now, x squared minus x minus the 2x that I'll bring over gives us minus 3x. And minus 2 will be minus 4 equals 0. Factoring that, I've got x minus 4, x plus 1 equals 0. So I've got possible solutions at x equals 4, x equals -1. In case 2, I distribute the negative through. So I've got negative x squared plus x plus 2 equals 2x plus 2. Now I'd like to get a positive x squared if I can, so I'll move things to the right-hand side here. So I've got x squared. The minus x will subtract from the 2x when I bring it over, so it's just a plus x here. And the 2 minus 2 will be 0, so I'll just have x squared plus x. There's a common factor of x here, so I just factor that out. And therefore, x is equal to 0 or x is equal to -1. So I get that -1 in both cases. I've done the checks here, so x equals -1 balances, so does 0, and so does 4. So they're all solutions. In conclusion, when algebraically solving an absolute value equation of the form absolute value of an expression, we'll call expression 1 equals expression 2, consider your 2 cases. Solve the equation in each case and check solutions in the original equation to see if there are extraneous roots. Note, I did not use the restrictions in a piecewise function, didn't cover it, and it's left for your classroom teacher to do with you.